Hey everybody, we're live and in studio. So up until now, we're done with the naming for alkenes. We're done with the namings for haloalkenes. We're done with the namings for alcohols. Obviously, we've learned structural isomerism for them. We're done with carboxylic acid. And today we're going to learn some new families which you've never come across in O levels and IGCSE, right? But before we dive into those new families, there are quite a couple of students who are catching on to something sneaky I did in the last, I think the previous class or the class before the previous class, which was I gave you guys a compound which looked something like this, and I said, hey, if you have a tie between the alkyl groups, I gave you guys this compound, this structure, and I said, hey, if you have a tie between the alkyl groups, for example, if you check this fella, it's 1, 2, 3, 4, 5, and if you go from right to left, it's 1, 2, 3, 4, 5, and there's a tie, it's a 5 carbon chain, and you have a tie between these two alkyl groups. You either have 2, 4, right, 2 and 4, or you have 2 and 4. So that's the tie. It's 6 in total, right? 2 plus 4, that's 6. 2 plus 4, that's 6. And the problem is one is ethyl, one is methyl. So which fella do you give the smaller number to? The one that comes first in the alphabetical order, which is 2. So it should be called 2 ethyl, 4 methyl, and then pentane, right? But everybody caught on to this, so I have to just clarify it. I just wanted to teach you guys this concept because a lot of students say, no, sir, don't be sneaky. It's meth, eth, pro, but, pent, hex. This is the longest carbon chain. So you try to be sneaky with us. I was like, okay, I just wanted to teach you a concept, guys. Relax. So let's clarify this. It was just to teach you guys a concept. You can draw something like this if you want. C2H5 right here, and then you have CH3. I hope now you are happy because now you have selected the longest carbon chain. You start numbering from left to right. You get what? 1, 2, 3, 4, 5, 6. These are 6 carbons, and then you get 1, 2, 3, 4, 5, 6. These are also 6 carbons in the parent chain. Now the problem is that if you start left to right, you get 3 to ethyl and 4 to methyl. And if you guys start numbering from right to left, you get 3 to methyl and 4 to ethyl, right? And there's a tie between these substituents. The chain is the same. When there's a tie between these substituents, which one do you, both give you 7, right? 4 plus 3 is 7, 3 plus 4, that's 7. So which do you give the smaller number to? Which numbering is correct? Obviously, the above numbering is correct. This left to right, because you want to give the smaller number to the fella which comes first in the alphabetical order, which is E, rather than give 3 to methyl. We give 3 to ethyl only when there's a tie between substituents. So yes, you all caught on to this. This is meth, eth, pro, but, pent, hex. But the reason why we selected this and we named it incorrectly was just to teach you guys a concept. So I hope this is clear. Everybody is messaging me separately. So that wait, and I'm like, okay, my God, I've taught these students a little too well. Right? So I wanted to clarify this. It was just to teach you a concept. I never thought that you guys would catch on to it, but since you have, let's switch the molecule for you. Okay, done. Now today what we are going to do is, instead of changing the recording of the last class, I just wanted to clarify it in this, right? So today we are going to learn some new families, and those two new families which we are going to do today are called aldehydes and ketones. Remember, we will study every single family in a lot of detail later on. This is just the basics for organic chemistry. I just want to teach you guys naming, right? So I'll only teach you guys stuff which is enough for naming. I'll teach you guys the ideas, the concepts, the naming bit, only to the extent of isomerism, only to the extent of naming for now. You have to learn a lot of other details for every single family. We are not done with alkanes. We aren't done with alcohols, alloalkanes. There's a hell lot of stuff in all of these families, right? But the reason why we're just skimming over them is to learn naming and learn isomerism, because without naming and isomerism, you can't move forward with even a single family in organic chemistry. So teachers who teach you guys a particular family in its utmost detail since the get-go, they are doing you guys injustice, because you won't be able to solve questions for organic chemistry if you study each chapter separately. So first you have to go over the namings, you have to go over isomerism, you have to go over a general idea of every single family, and only then and only then will you be able to understand the mechanisms and everything in every single family, right? So Aldehydes and ketones. This is something new which you haven't come across in O levels and IGCSE. You have never heard these names, aldehydes and ketones. Obviously you must have heard alkanes, haloalkanes or halogenoalkanes, alcohols, carboxylic acids. You've heard them before, you know how to draw them, and we've also recapped how to draw them. We've learned the difference between displayed formula, skeletal formula, structural formula, molecular formula, general formula, and so on and so forth, right? So we've learned all of these things for these fellas even in O levels and IGCSE, and we've recapped it. Right now, these two families are something which are new in AS level chemistry. Now, what are aldehydes and ketones? A couple of things you need to know about these aldehydes and these ketones are that they are both carbonyl compounds. They're both carbonyl compounds. What does that mean? That means they both have C double bonded to O. This particular fella right here, C double bonded to O, this is called carbonyl, right? Some teachers, when I was your age, I used to call this carbonyl carbon. Normally scientists who are like me, they call it carbonyl carbon. It just sounds fun. Carbonyl carbon, or you could just call it carbonyl, right? So these are carbonyl compounds, which means that whenever you see an aldehyde or whenever you see a ketone, you will see this fella right there, carbonyl carbon. But remember, do not confuse it with carboxylic acids. Carboxylic acids also have carbonyl. You are absolutely right. It also has carbonyl, but it also has the OH bond right here. So it has carbonyl, but it also has this OH bond here. And you know what this fella is called? This is called carboxyl. And that's the name of my YouTube channel. So what actually happened was that when I was making my YouTube channel, I wanted to name my YouTube channel Hydroxyl. And what fella is hydroxyl? Hydroxyl is the OH group of atoms. But my brother said, no, Suleiman, name your YouTube channel Carbonyl, right? So carbonyl is this fella right here. And the problem was that when I wanted to name it Carbonyl, there were quite a couple of YouTube channels by the name Carbonyl. Obviously, I don't know what they are for, but there were quite a couple of channels which were called Carbonyl, right? And I wanted to call it hydroxyl for the same purpose. My brother said, no, Carbonyl sounds better. I was like, no, hydroxyl sounds better. I was like, okay, brother mine, let's combine these two. So whenever C double bonded to O combines with the OH group of atoms, this is basically then called carboxyl. So this is the reason why my YouTube channel is called Carboxyl, because my brother and I couldn't decide whether we should name this channel Hydroxyl or Carbonyl. So we just combined the two. We said, hey, let's just call it Carboxyl. You'll be happy, I'll be happy, right? So aldehydes and ketones have the carbonyl group of atoms, right? It has C double bonded to O, but they're fundamentally different from each other. They're different families, right? And if you haven't seen aldehydes and ketones in real life, I'll tell you, you have seen them, you just don't know whether you've seen them or not. These are so widely used in perfumes. If any of you were to ever start your perfume brands, you need to know about aldehydes and ketones. Aldehydes or ketones are used in almost every single perfume on the face of planet Earth. Obviously, the perfumes which are on the expensive side, on the premium side, right? So these are widely used in perfumes, just like esters. Remember esters when you used to study them in O levels and IGCSE? Just like esters were used in food flavoring or in perfumes and solvents and so on and so forth, aldehydes have similar uses. They are also used in perfumes, widely used in perfumes, right? But they are fundamentally different from each other. They're both carbonyl compounds, but fundamentally they are different from each other. So what do you mean fundamentally they are different from each other? Basically, if you look at an aldehyde, yes sir, the aldehyde has the C double bonded to O group of atoms. You are absolutely right. And this is also going to be present in a ketone. They are both carbonyl compounds. But the beauty for an aldehyde is that an aldehyde has the carbonyl group of atoms, but it will always have this H right here. It'll have the carbonyl group of atoms bonded to AH. It'll always have the carbonyl group of atoms bonded to H. Unlike in carboxylic acid, where the carbonyl group of atoms is bonded to the OH, right? Unlike this, in aldehydes, the carbonyl group of atoms is bonded to H. And then this C, obviously it can make 4 bonds. So it makes 2 bond here, 1 bond here, and it can make 1 more bond, and that we call that the other bond is going to be with the R group. Similarly, just like in carboxylic acid, we said that this other bond can be with the R group of atoms, which means this R can either be hydrogen in case of methanoic acid, or this can be any alkyl group, any alkyl. It can be CH3, CH2, it can be CH3, CH2, CH2, and so on and so forth, right? So this R group of atoms can be a hydrogen and it can be alkyl. It's just a generic way of saying this R can be literally either a hydrogen bond or a carbon bond, right? A carbon bonded to hydrogens or another carbon bonded to it. It can be a chain of carbons being bonded to this particular fella right here. So this R is just a general way of referring to either a hydrogen bond or an alkyl bond. Similarly, aldehydes, whenever you see R, it represents either a hydrogen bond or an alkyl group of atoms. And in this particular fella, this R represents, normally it does represent that, right? And this R represents the same in this fella. It either represents a hydrogen or it represents any alkyl group of atoms. So if I ask you, sir, how do you draw aldehydes? How do you draw aldehydes? Obviously, you now know how to draw them. Without me telling you anything, you can easily draw them. Just like when we were able to draw carboxylic acids, the idea is the same. You first draw the functional group and then you see how many carbons you need to add. And, based on that, you start adding the carbons here and then you bond it with hydrogens, right? So, for example, in carboxylic acid in the last class, we learned that if you have a C double bonded to OOH and you want just one carbon carboxylic acid, you just bond it to the H because you already have one carbon right here. But if you have a 2-carbon carboxylic acid, you draw the functional group which is C double bonded to OOH carboxyl, and then you bond it to, because there are 2 carbons, you've already drawn one, you bond it to another carbon, and then you complete the bonds with hydrogen. Similarly, if you have a 3-carbon carboxylic acid, again the idea is the same. Draw the functional group always, and then you need 3 carbons, you've drawn one, so bond it to another carbon, bond it to another carbon, tuck, 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 complete the bonds with hydrogen. Just like that, it's very simple to draw aldehydes as well. You draw the functional group, which is this fella right here. It's the C double bonded to O bonded to a H, right? So this is the functional group. But whenever they ask you to, show the functional group, you say R bonded to C double bonded to O bonded to H, or you can just show the functional group like this. You put a hyphen, and then you put CHO, which is, this fella, this carbon can be bonded to anything else, it can be bonded to a hydrogen or an alkyl group of atoms, or you can write R instead of this, it's up to you. But this bond right here will always be present in an aldehyde, CHO. Now the problem is, a lot of students will come at me and they're gonna say, sir, don't be sneaky again, Okay, well, I'm not being sneaky, what do you mean? Sir, this carbon is bonded to an O which is bonded to a H, right? So why aren't you saying this is COH? That's the question that a lot of students ask me. Sir, why aren't you writing it as COH rather than writing it as CHO? Why don't you write it as COH? And the answer to that is very simple. IUPAC does not allow me to do that. International Union of Pure and Applied Chemistry says no, you don't write it like this, right? That's the simple answer for it. Your naming body says you can't write it like this. That's the simple answer. But there's logic behind why they say you can't write it like this. Because the problem is that you want to differentiate between alcohols and aldehydes. And you know that alcohols have the OH group of atoms, right? So if you were to write COH, it could confuse a scientist in thinking that it's not an aldehyde, rather it's an alcohol. So how do you show a differentiation between aldehydes and alcohol? You write aldehydes as CHO rather than COH. But whenever you have an alcohol, you write it as COH, right? So alcohol group of atoms is the OH group of atoms, and aldehyde group of atoms is the C double bonded to O, the carbon bonded to the H group of atoms, right? So just to differentiate between aldehydes and alcohols, they said that, hey, although we know that carbon is bonded to carbon and carbon is right here, carbon is double bonded to O, which is bonded to the H. This is the idea, it's COH, but we write it as CHO to indicate that this is an aldehyde and to not be confused between aldehydes and alcohols. I hope this is very, very clear. So CHO does not mean it's carbon bonded to a hydrogen which is bonded to O. This is practically not possible because hydrogen can't make more than one bond, right? It's very logical. It's like a puzzle. You can't make more than one bond for hydrogen. So writing CHO is absurd, but IUPAC said no. Although it's absurd, we want to differentiate between alcohols and aldehydes. We don't want to confuse it with aldehydes. So whenever we write CHO, understand that we are talking about C bond double bonded to O, which is bonded to the H, which is carbon bonded to a H, right? I hope this is clear. Now the question is, how do you draw them? Just like you draw carboxylic acids, it's a piece of cake. If you know the functional group for aldehydes, you can draw them and it's going to be a piece of cake. The functional group is the C double bonded to O bonded to the H group of atoms. It's the CHO group of atoms, right? That's the functional group for any aldehyde. So now you tell me, if you were to draw 1 carbon aldehyde, a 2 carbon aldehyde, a 3 carbon aldehyde without knowing anything about aldehydes, are you able to draw them? Absolutely. There's already 1 carbon here, so what should the R represent? R should be a hydrogen. I can't add more than 1 carbon. 1 is already present. This is a 1 carbon aldehyde. So how easy. And if you were to draw a 2 carbon aldehydes, you draw the functional group first, and then you need 2 carbons. You've already had drawn 1, you just need 1 more, 1, and then complete the bonds with hydrogen. Tuck, 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 and that's it. A 3 carbon aldehyde, C double bonded to O bonded to H. That's the group of atoms that you need for an aldehyde, and you need 3 carbons, so tuck, and then this is H. Similarly, 4 carbons, C double bonded to OH, that's the group of atoms for any aldehyde. And obviously, this is only possible on terminal carbons. You can draw them at the rightmost side or on the leftmost side. You can draw this fella on any middle carbon. And the reason for that is pretty simple. You can draw it on any middle carbon can be your carbonyl carbon. Because if it's on this middle carbon right here, the middle carbon would then be bonded to C and C. And this wouldn't be an aldehyde, because for it to be an aldehyde, the carbonyl carbon must be bonded to a hydrogen, and the only possibility for this is that if it's on the terminal carbons, which is either it's going to be on the rightmost carbon or the leftmost carbon, the middle carbon can't be C double bonded to O. In 3 carbon chain, if this is the C double bonded to O, it can be bonded to H on any side, right? It'll be bonded to a carbon and another carbon. So it's not going to be an aldehyde. For an aldehyde, you need this right here. Just like in carboxylic acid, you needed C double bonded to OOH. That's why carboxylic acids were also on terminal carbons. This functional group was present on terminal carbons. So just like that, aldehydes are also present on terminal carbons. And so 4 carbon aldehyde, tuck, tuck, and that's a piece of cake. Skeletal for it, a piece of cake again. Let's draw skeletal in reverse working. You have 4 carbons, so 2, 3, 4, and on the last carbon you have carbon double bonded to O, and that's it. Remember, we don't draw any hydrogens which are directly bonded to carbons. No, that's it. That's skeletal for it. Then 3 carbons, tuck 2, 3, 2, 3, and then you need a carbonyl carbon on the terminal, and that's it. Then 2 carbons, tuck 2 carbons, and that's carbonyl carbon. That's a 2 carbon aldehyde right here. And then 1 carbon, oh, that's the 1 carbon aldehyde, but you'll never be asked to draw 1 carbon aldehyde in skeletal. It's practically, it's absurd. That's the 1 carbon aldehyde. That's there. Right? So that's the idea. Now the question is, sir, how do you name aldehydes? Okay, enough about drawing them. How do you name them? Again, just like you were naming alcohols, just like you were naming carboxylic acids, we always use an alkane as the reference point. So alkane was the reference point whenever we used to name alcohols. What did we used to do? We took the, you take the man out of my, we took the E in alkane and added the OL, and obviously we added the position of the functional group here. Just like that, when we were also studying about carboxylic acid, how did we name carboxylic acids? We took alkanes as the reference point, removed the E, add the OIC, and added acids. So it was alkanoic acid effectively, right? Which was, if you had methane, it would be methanoic acid, ethane, ethanoic acid, and so on and so forth. So how do you name aldehydes then? Aldehydes, a piece of cake. Naming, take alkanes as the reference point. And I always take alkane as the reference point because it's easier, to remember them as well. Take alkanes as the reference point. Instead of an E, add the Al. That's it. So if you were to name the 1 carbon aldehyde, it would be called methane. No, it wouldn't be called methane. Why? Because the E would cut off and the Al would be replaced with the Al. Right? So it will not be called methane, it will be called methanol. Right? If you were to name a 2 carbon aldehyde, the E would cut off and you would call it ethanol. Right? A 3 carbon, it's not going to be called propane, the E would cut off, it will be called propanol. And then 4 carbon, I think you got the hang of it, butanol. Right? 5 carbon, write the spelling of pentane, but instead of an E, write an Al. So pentanol, hexanol, heptanol, octanol, nonanol, decanol, right? And so on and so forth. I get it should it should be on terminal, but what if me make carbon double bonded to another and there is hydrogen on other side, right? What do you mean? How many carbons, Huma? In how many carbons do you want to do that? You can unmute yourself and ask the question. It'll be better. Yes. Yeah, yeah, yeah. Yeah. Mm-hmm. Which for which particular fella? For the one carbon, two carbon, three carbon, four carbon fella? Which fella? Okay, for the three carbon fella, why you're saying why can't it be on the middle carbon? Let's try it out, Homa. Let's clear it by trying it out, right? Always we want to show you guys what's actually happening. It's like a puzzle. Homa is saying why not put the carbonyl carbon right here? Then Homa, you don't have any hydrogen on the left or on the right. What do? Carbon has already made four bonds. If you're saying, hey, can't it be like this? It's not possible because carbon can make a total of four bonds. So 2, 3, 4. Where can this fella come in? Now we got it. So it can't be on the middle one, right? So it has to be on the terminal side. Awesome. So that's how you draw them. That's how you name them. That's the skeletal for it, right? The skeletal, right here. That's the skeletal for it. Give me a moment. Alright guys, moving forward. Now, one thing you need to understand is that I'm not just prepping you for the Cambridge exams, I'm prepping you for the future. And in the future, you can be tested something like this. But normally when you talk about skeletals, for any aldehydes, you have to show the CHO bonds effectively. Although I said normally we don't show carbons directly being bonded to hydrogen, but because it's the functional group for this fella, normally in your exams, you basically show the hydrogen. It's essential for your exams effectively, but the examiner can, someday when the examiner wakes up and he does not show you the hydrogen bonds, know that if carbon is double bonded to the O and then it's bonded to the alkyl group here, the other bond is going to be obviously with hydrogen. So your examiner normally shows the hydrogen bonds in this particular fella in the CHO group of atoms. So in the skeletal formula, we're going to make certain amendments. I'm going to show this hydrogen bond right here. I'm going to show a hydrogen bond right here. I'm going to show a hydrogen bond right here and a hydrogen bond right here. It's basically this node is carbon double bonded to O, which is bonded to the hydrogen. That's 3, and then its fourth bond. So normally in the CHO group of atoms, we do show this hydrogen bond. We do show this hydrogen bond. We do show this hydrogen bonds. It's essential for your exams, right? But remember, if someday you wake up and the examiner has not shown you a hydrogen bonds, always look at the total number of bonds. This node is bonded to one alkyl, double bonded to O, so it's already bonded to 3. It has already made 3 bonds. This carbon has already made 3 bonds, so the fourth bond is automatically with a hydrogen. But your examiner says show that fourth bond with the hydrogen in case of CHO. Done. So that's also something you should keep in mind. So this is the better way of drawing it for your exams, the skeletals for it, right? So in skeletals, do show the CHO bond. The CHO bonds must be shown. Even if it's carbon directly bonded to a hydrogen, you must show that stuff. Done. Now, we're done with the naming, we're done with the skeletal, we're done with the displayed structure for it, we're done with the naming for it, we're done with how to, how many carbons you can have, 1, 2, 3, 4, 5, 6, and so on and so forth. And now we are going to look into the molecular formula for it. So in the molecular formula, again, just like in carboxylic acids, we were showing CH3, CH2, COOH. We were showing this COOH group of atoms separately, in molecular formula, HCOOH, and then you have CH3, COOH, and so on and so forth. We were showing these group of atoms separately, but when we talked about molecular formula in its utmost precision, if the examiner asked me what's the molecular formula for, a 2-carbon carboxylic acids, we summed it for the examiner. We said it's C2H, what H, how many H's? 4 H's and O2, right? So we summed it for the examiner rather than writing it like this. But when we were writing it in equations, we were writing it in the form of its structural formula, right? So even here, normally we show the CHO group of atoms separately. Normally we show the CHO group of atoms separately. But again, the examiner wants the molecular formula in a summed format. That's the reason you have to show it in the summed format. So if you look at this fella right here, you have HCOH, right? So it's basically H bonded to a CHO group of atoms. Remember, it's COH, but we write it as CHO. Why? Just to differentiate between alcohols. And again, because the examiner likes it in a combined format, we write CH2O as a one carbon aldehyde. Then if you were to write a 2-carbon aldehyde, look at this, 2 carbons, and then how many hydrogens do you have? 1, 2, 3, 4. 4 hydrogens and 1 oxygen. So 2 carbon, 4 hydrogens, and an oxygen, right? Then if you look at a 3-carbon aldehyde, it's how many carbons? 1, 2, 3, 3 carbons, 1, 2, 3, 4, 5, and 6. 3 carbons, 6 hydrogen, and 1 oxygen. So 3 carbons, 6 hydrogens, and 1 oxygen. And what you realize is, oh sorry, you have 2 carbons here, right? Why have I written CH4O? It's 2 carbons, C2H4O, right? So what you realize is you start to see a trend. Similarly, if you were to write for butanol, it's meth, eth, pro, but. Butanol is 4 carbons. How many hydrogens do you have? How many hydrogens do you have? Count it out. 1, 2, 3, 4, 5, 6, 7, 8. You have 8 hydrogens. So it's C4, H8, and O. And what you realize is, hey, the number of hydrogens are twice the number of carbon. The number of hydrogens are twice the number of carbon. The number of hydrogens are twice the number of carbon. So if you were to figure out a general formula for any aldehyde, what would it be? It would be, hey, if you have n number of carbons, because we know general formula is the molecular formula, but in terms of n. So if you have n number of carbons, hydrogens are twice that number. So hydrogens are twice the number of n. And how many O's do you have? 1 O. So this is effectively the general formula for any aldehyde. If I write, say, is this fella an aldehyde? C40H80O. Is this an aldehyde? Yes, it's an aldehyde. Why? Because it fits the general formula of an aldehyde, which is CnH2NO. And you can even plug it for the examiner. C40H2 times 40 is 80, and then you add an O right here. Done and dusted. Done. Sir, you're so Gen Z coded. How am I Gen Z coded? I haven't even said anything. Sir, no. Fatima, no. बायो की टीचर से पूछना पड़ेगा. देखेंगे स्ट्रक्चर को देखें, नजर आ रहे तो होगी. But I don't think so. Acha, done. So that's something you needed to know about aldehydes. What we learned was how to draw the skeletal for it, and then we learned it's the CHO group of atoms, which is the functional group, CHO bonded to R. We learned how to name them, we learned the molecular formulas for it, and we learned the general formulas for it, right? Now, next, we're going to learn something known as ketones, right? So, ketones. Again, this is I'm only teaching you guys, I'm giving you a brief idea. Brief idea. We haven't talked about structural formula, my bad. Let's also talk about structural formula. In the structural formula, again, treat each unit separately. There's a hydrogen bonded to a COH, right? So hydrogen being bonded to a COH. What's the problem with this? Be quick. Hydrogen being bonded to COH. Is this the correct way of writing the structural formula for an aldehyde? It should be the correct way, because see, C is first being bonded to O and then being bonded to H. Isn't that correct? COH. Is this the structural formula? The answer to that is no, it's not the structural formula, because IUPAC said no, you can't write it like this. Why? Because they wanted to differentiate between alcohol group of atoms, which is the OH, and the aldehydes. So the structural formula for it is HCOCHO, not HCOH. And these are the tiny things which either confuse students or make them crystal clear in their concepts. Sometimes in the exam, they say this is a compound, C, H bonded to AC, which is bonded to O, which is bonded to H, and students think that it's the, this C bonded to H bonded to O, and students think, hey, carbon can't be directly bonded to hydrogen, so it must be COH, and then they try to draw this COH, and I'm like, oh, you dumbos, this is the aldehyde group of atoms. That's the functional group of an aldehyde. So just be very careful in these teeny concepts, right? Now, next. So structural formula for the first carbon is right here. I hope you guys can now do it. This is CH3 and CHO. So the second carbon's structural formula is what? CH3, CHO. Then the third carbon is what? CH3, CH2, CHO, and so on and so forth, right? CH3, CH2, CHO. Normally in equations we write the structural formula for aldehydes even. Done? So I hope you guys know that aldehydes are the carbonyl group of atoms. They're normally used in perfumes. How do you name them? Instead of an E, you call the AL. So methanol, ethanol, propanol, butanol, and so on and so forth, right? Now let's talk about ketones. Ketones are also carbonyl compounds. Ketones are also carbonyl compounds. What about isomers of aldehydes? Hold on a minute, Ibrahim. Hold your horses. They both of them are connected, so I have to teach you guys ketones as well, right? Okay. So ketones are also the carbonyl group of atoms, and they are also bonded to R, and it's also bonded to H. No, it's not bonded to H right here. That's the difference between ketones and aldehydes. For any compound to be a ketone, it must have a carbonyl group of atoms bonded to the R, just like in aldehydes. The carbonyl group of atoms was bonded to the R, and then you needed to know that this bond was always with hydrogen for it to be an aldehyde. For this fella to be an aldehyde, the carbonyl carbon must have at least one bond with a hydrogen. It can have also two, that will be methanol, but at least one bond should be with hydrogens. Ketones are a little different. They're fundamentally different from each other, because although ketones also have the carbonyl carbon bonded to the R group, right here, carbonyl carbon bonded to the R, this R is right here even in aldehydes. But the problem is that in ketones, the carbonyl carbon is bonded to the R, but it's not bonded to H. Then what is it bonded to? It's bonded to another R. It's bonded to another R, or you can call it R dash or R prime. It doesn't make a difference, right? So this carbonyl carbon, for it to be a ketone, it must be bonded to either an R here and another R here. It can't have any hydrogen bonds. So what you realize is that this is the only case where the R group only represents alkyls. The R group cannot be a hydrogen bond. Nah, then it won't be a ketone. If the R group is a hydrogen bond, then it would again become an aldehyde. Because if you put a C double bonded to O bonded to an R, which is CH3 maybe, or CH3CH2, whatever it is, you'll realize that if you put a hydrogen bond here, it'll convert into aldehyde. So this R cannot be a hydrogen bond in case of ketone. Both R and R prime, R and R dash, they are both alkyls. And what you realize is that means that the first ketone that you're going to have is going to be carbonyl carbon bonded to a C and bonded to a C. This is the smallest ketone possible, which is what? This is the smallest ketone possible, which is a 3-carbon ketone. So the smallest ketone that exists in this planet is a 3-carbon ketone. It's CH3 bonded to a C double bonded to O, carbonyl carbon, which is bonded to CH3. This is the smallest ketone possible. The smallest ketone possible is a 3-carbon ketone. There is no such thing as a 2-carbon ketone. Why? Because if it's a 2-carbon compound, the problem is that you have 2 carbons right here. So the 4th bond must automatically then be with hydrogen, and this is no longer a ketone. This is what? This becomes an aldehyde, a 2-carbon aldehyde, right? Because the moment carbonyl carbon is bonded, any of the bond of carbonyl carbon is with hydrogen, it automatically is an aldehyde, not a ketone. For it to be a ketone, both bonds must be with alkyl group of atoms. So the smallest ketone, alkanone, is basically a 3-carbon alkanone or a 3-carbon ketone. And how do you name them? You name it like this. You take the naming of an alkane, instead of the E, you add the 1 to it. So instead of an E, it is 1. Just like in aldehydes, instead of the E, you added the Al. Here, instead of the E, you add 1 to it. I'm using alkanes as a reference point to teach you all types of naming. So you take the name of an alkene, add 1. Instead of the E, add 1. So if I have a 3-carbon alkanone or a 3-carbon ketone, what do you call it? Or a 1-carbon ketone. What's a 1-carbon ketone called, guys? What's a 1-carbon ketone called? Methane, right? Methane. And instead of the E, you replace it with the ONE, right? Everybody agrees with me? Methanone, right? Methanone, a 1-carbon ketone. Yes, methanone. And that is where Sir Suleiman is known. That is what Sir Suleiman is known for his testers. So I threw a curveball at you, and a lot of people are like, yeah, sir. Jaye chat se chalang mare mar mur. I'm joking. Don't jump off the top of a roof. But a 1-carbon alkanone, a 1-carbon ketone does not exist, you dumbo jumbo. There's no such thing as methanone. There's no such thing as ethanone. The smallest ketone on the face of planet Earth is called propanone, please. So it's propane, and instead of an E, you add the 1. So it's called propanone. That's it. So propanone, butanone, pentanone, hexanone, nonanone, so on and so forth. Heptanone, octanone, nonanone, decanone, and so on and so forth, right? Now, the question is, how do you draw them? So we've learned the naming. How do you draw them? Right? Propanone, yeah, sir, do naming for us. Butane ki jagah, come on, you guys aren't, in grade 2 anymore. I hope you guys can do it. We have a lot of more things and a lot of other things that we need to cover which are far more important. But butane ki jagah, instead of the E, add the ONE. I've taught you the concept. Now you can name them butanone. Similarly, instead of the E, add the ONE. So it's pentanone, and so on and so forth. Guys, please don't make me name all the 10, all the first 10 ketones. I hope you guys can do it on your own. Name the alkene for it, the respective alkene. Instead of the E, put the ONE. That's it. So propanone, butanone, pentanone, hexanone, heptanone, octanone, nonanone, decanone, and so on and so forth. Right? Now, the question is, how do you draw them? Again, the smallest ketone possible is C double bonded to O, which is CH3 right here, and CH3, right? And remember, see, if I am the examiner, I would likely deduct a mark, but Cambridge normally doesn't, but be on the safer side. Cambridge is moving towards a very, very conceptual approach, and so if you guys draw it like this, there's no such problem in drawing it like this, but there's gonna be, a slight misunderstanding. Cambridge might think that you are confused between the bond. Cambridge examiner might think that you are saying that carbon is bonded to the hydrogen, which is bonded to the carbon, which is absolutely incorrect. We also know hydrogen can only make one bond. So instead of writing it like this on the left side, right is correct, right? You see, you're first showing the carbon bond and then you're showing the hydrogen bonds. On the right side, you're first showing the carbon-carbon bond and then you're showing the hydrogen bond. But on the left side, you're doing a mistake. You're putting the carbon and the hydrogen bond and then the hydrogen and carbon bond. So it's better to show it like this. You show the carbon bond and put hydrogens, and there are 3 hydrogens. See? And now I normally do it like this. Now you know. You can also now do it like this. CH3, this is the correct or the better way of showing it rather than this. This may also give you the mark for it, but again, don't be on the safer side. Be on the safer side. You never know with the examiner. The examiner changes from time to time. So you might have a more conceptual examiner and he might deduct a mark if you write it like this. These tips are very important. Beta koi nahi batata ye baatein aapko. Right? Don't even tell you these things. Except for me. Yeah. The reels that you guys keep on sending me. Shame. Okay. And then if you were to draw a 4-carbon ketonone, how a ketone or alkanone, how would you draw a 4-carbon ketone? So carbonyl-carbon bonded to a CH3. These are 2 carbons, and I want to draw 4. So there must be a CH3 right here, right? So 1, 2, 3. I've already drawn 3. Let's just draw another one, CH2, right here. Right? Or you can write it like this, couldn't care less. You can write it like this, or you could put the C first and then the H2s, right? That's also possible. But then you would put a C first and C first and then the H's, right? So you could write it either like this, or you could just show the displayed version of it. It's up to you. CH3, CH2, CH3, like this, right? So it's a 4-carbon ketone. Sir, but you just said don't do it like this. Okay, you can write it like this, man. I couldn't care less. You can write it like this. CH2s and CH3s. You can show it like this. But this becomes a little awkward. So here the examiner should use his brain and tell you, yeah, this is the correct way of it. Normally this is nothing, right? This is neither the displayed formula nor is it the structural formula. This is just a way of showing it. Because in displayed formula you show all the bonds. In structural formula you show no bonds except for the carbon-carbon double bond or the triple bond, right? So that's the displayed version for it. A 5-carbon displayed version would look something like this. CH3, CH2, CH2, C double bonded to O, CH3 right here. Or you could have switched the place. You could have put a CH2 right here. It's up to you. Up to you. Now, the problem is, if I were to start, writing the molecular formulas for it, what do we do? What we do is we count the number of carbons, 4 carbons, count the number of hydrogens. Let's start with the 3 one. So count carbons, 3 carbons, C3. Then count hydrogens, sir, 6 hydrogens and an O. Then for 4, you have 4 carbons, count the hydrogens, so 3, 4, 5, 6, 7, 8. 8 hydrogens and an O. Count the carbons, 5 carbons, 10 hydrogens and an O. And you've seen something like this. This is the molecular formula for it. And you've seen something like this before. C3H6O, C4H8O, right here. C3H6O, C4H8O. That's why I said aldehydes and ketones are connected through their molecular formulas. So C3H6O or C4H8O or C5H10O, these are Also, this is also the way aldehydes are written. And what you realize is, if I were to write a general formula for any ketone, I would know that, hey, it follows the same trend as an aldehyde. The number of carbons you have, the number of hydrogens are twice the number of carbons and O. So it's basically what? CnH2n and O. It's basically carbons. If you have n number of carbons, hydrogens will be twice the number of that and O. And this is also the general formula for a ketone. So realize that a ketone and an aldehyde are literally having the same general formula, but they are fundamentally different. The functional group is fundamentally different. This is the CHO group of atoms, and this is basically the CO bonded to the R's, right? It's basically C double bonded to O bonded to R and R dash. That's the idea behind it, where R and R dash are only alkyls. It can't be a hydrogen. So fundamentally you realize that they both have the same molecular formula, but their structures are different. And that's what you see, and that's what you see and observe and use your brain a little. That's when you see and observe and use your brain a little, that hey, ketones and aldehydes are basically structural isomers of each other. And which particular structural isomers? Sir, they are functional group isomers of each other. But remember, ketone starts with 3 carbons. The smallest ketone is of 3 carbons, propanone. So what you realize is propanone and propanal, they are both isomers of each other. Remember, always, if you have if you have an isomer or not, whatever the case is, an aldehyde has at least one other fella which has the same molecular formula. Always it'll have a fella which has the same molecular formula but different structural formula, and that'll be the respective ketone for it. So for example, if I were to draw a 3 carbon propanone, how would it look like? Tuck 2 3, and that's a 3 carbon propanone right here. CH3 bond here, CH3 bonds here, and in the middle carbon you have the C double bonded to O right here. But if I were to draw a 3 carbon aldehyde, it would be what? You tuck 2 3, and because it's an aldehyde, it's C double bonded to O, and we show the H as well. So if you count the number of carbons and hydrogens, you will see that both will give you 3 carbons, 6 hydrogens, and 1 O, and these are both isomers of each other, and they are functional group isomers. Does the examiner require you to know the number of functional group isomers for each particular fella? No. Remember, when the examiner always tests the structural formula, the isomers, the structural isomers for particular compounds, they want you to ignore the functional group isomers for that fella. Only chain them, only position them. They want you guys to ignore functional group isomers. But this is something you need to know. This can be tested in the exam. For example, they give you a propanone and they say which of these fellas is the isomer for it. So instead of counting all the carbons and all the hydrogens, you say, hey, for propanone, the respective functional group isomer is going to be what? Is going to be propanal. For butanone, the respective functional group isomer will be butanal. For pentanone, the respective functional group isomer will be what? For pentanone, pentanal, right? So it'll always have one functional group, and that's why they are similar with each other. They have the same molecular formula, same general formula, but you understand that they're fundamentally different. Aldehydes has the functional group of CHO, whereas the ketones have a functional group of carbon bonded to 2 R groups, right? So if the examiner says write the functional group or draw the functional group for any ketone, it's basically carbon bonded to R and R dash. That's what you show the examiner. But if it says write the functional group for any aldehydes, it's the CHO group of atoms. That's it. Or you could show it C double bonded to O, H and R. Both are the correct ways. You can write it like this for the examiner and say R is an alkyl group. Hydrogen / alkyl group of atoms. Right? Done. And where R is alkyl group only, no hydrogens. It can't be hydrogen. Done. Now the question is, if I give you something known as this C3H6O, if I show you something like this, is this a ketone or is this an aldehyde? Remember, you can't actually tell. If I just give you the molecular formula, which is C3H6O, is it a ketone or is it an aldehyde? I can't tell. I can't. It can either be a ketone or it can be an aldehyde. I don't know. Can be a ketone, can be an aldehyde. I don't know. Right? Then how do we distinguish between the two? Later. Just like you used to distinguish between an alkane and an alkene. But that was easy, Remember, in O-levels IGCSE, you learned something known as bromination or bromine liquid test or bromine aqueous test. Here, when we start to learn these groups in quite a lot of detail, you learn how to distinguish between the two and so on. And for now, I'm just building your brain cells. And okay, they have the same molecular formula, they have different functional group, and therefore they have different structural formulas. But then, if their molecular formula is same, how do we distinguish? I'm just, creating that curiosity in your brain that this is also possible, that's also possible, this is also possible, right? But when we now look at ketones in a little detail, let's start to summarize things for ketones. So if I were to name a 1 carbon ketone, a 2 carbon ketone, a 3 carbon ketone, a 4 carbon ketone, and a 5 carbon ketone, how do I do that? What is a 1 carbon ketone known as? Methanone, right? Name it as an alkane. Instead of the E, add the O-N-E. Oh no, you dumbo jumbo, why are you saying methanone again? Methanone is not possible. Ethanone is not possible. The smallest ketone that you have is what? A 3 carbon ketone, which is what? It is C double bonded to O, bonded to a CH3, bonded to a CH3 right here. And that is what? This is meth eth prop. This is propanone. What are you doing, man? What are you doing? Please. Methanone and ethanone are not possible. Please ensure that. What's the functional group of a ketone? It's carbonyl-carbon bonded to R and R dash, where R and R dash are alkyl groups. And only. Tayyiba is saying, Sarji, we know methanone and ethanone don't exist. No, Tayyiba, a student, I'm not going to name him, he just literally said. तो क्या करूं? No, sorry, she. Right? Then, propanone, butanone, pentanone, and so on. Remember, if you mess up the spelling, you don't get any mark. Right? Now, how do you draw the skeletal for it? How do you draw the skeletal for it? Again, propanone, tuck, tuck, 3, and the skeletal is tuck, tuck, tuck. Butanone, meth, eth, pro, but, and you could put the double bond right here or right here. I couldn't care less. Then pentanone, tuck 2, 3, 4, 5. You can put the double bond on any carbon. For now, I couldn't care. Right? So that's pentanone. Done and dusted. And then let's look at the structural formula for it. Look at how do we write the structural formula. See, it's CH3, CO, CH3. So the structural formula is CH3, CO, CH3. Right? Similarly here, CH3, CO, CH2, CH3. CH3, CO, CH2, CH3. And that's the fundamental difference between the two. Because if I were to write the structural formula for an aldehyde with 3 carbons, how would that look? With 3 carbons, 2, 3. This is the skeletal for an aldehyde with 3 carbons. 1, 2, 3. Right? So it's basically what? It's CH3, CH2, and CHO. Look at the fundamental difference between the two. And this is what you need to see with your naked eyes. If you see this, that's a ketone. If you see this, that's an aldehyde. So these are things that you need to visualize now. These are things you have to visualize. A 4 carbon aldehyde. 2, 3, 4. And put a double bond and a H here. Right here. So it's 1, 2, 3, 4. 4 carbons. And if you were to write the skeletal for it, CH3, CH2, CH2, CHO. So CH3, CH2, CH2, CHO. Look at the difference, the fundamental difference between the two. How different are they? They are quite different, aren't they? Right? So skeletals drawn, structural formula written, everything done. Right? Now the question is, how do you properly name them? Naming of ketones and aldehydes. Again, the same method. We are going to use the same method, but remember, ignore the functional group isomers. You always know that whenever you have ketones and aldehydes, they are both functional group isomers of each other. So there will be 2 isomers always for aldehydes above 3 carbons, right? There'll always be 2 isomers, at least 2 isomers, because we know functional group isomerism exists, but we are going to ignore them. If the examiner asks us, write the structural isomers for, a ketone which has 4 carbons, I am going to ignore functional group isomers for it, please. This is not the requirement of any examiner. He wants you to ignore functional group isomers, which is pathetic. If you're asking me isomers, I will tell you functional group isomers, but the examiner says there can be so many possibilities then that, as you move forward, there can be so many possibilities that you can't really tell. There can be functional group isomers with something else, with something else, with something else. So, the students are not robots. They can't sit down thinking about all the possibilities. That's why they tell you to ignore them. So if you ignore them, it becomes very simple. You just either change the position of the functional group, or what do you do? You either change the position of a functional group or you change the chain. So CAN method, CAN, chain, which is 4 carbons, tuck, 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 3 carbons, 2 and 1, and then add-ons. Let's suppose a 4 carbon ketone is there. So add-on is the double bonded to O. So you could place the double bonded to O on the first carbon, this fella, or you could place the double bonded to O on the second carbon, this fella. You could show it like 2, 3, 4. On the first carbon, you could show the double bond right here. And you could show the double bond 2, 3, 4 on the second carbon right here. So what would be the name? The name would be meth-eth-pro but. So butanone. But remember, butane, O-N-E. But between the but and the O-N-E, what do? We write the position of the functional group. No? Oh, where did it go? Something happened right here. So we write the position of the functional group, which is on which carbon? It's 1, 2, 3, 4. We start numbering from the side where the functional group is the closest. So C double bonded to O is right here on the second carbon. So it's butan 2-on. Right? Butan 2-on. And this fella is what? The 1 carbon. This fella right here. This is meth-eth-pro butan 1-on. It's butanone, but butan 1-on. That's it. So 2 carbons here, and then this fella can exist. Yeah, this fella can also exist. Right here. CH3, and then you place a double bond right here. Remember, the double bond can't be on the first carbon. No, the double bond can't be on the first carbon, because if it's on the first carbon, then there's a problem. And this is what you guys didn't see. If the double bond was on the first carbon, now that's a problem. It can't be butan 1-on, can it? Sir, please use your brains. Ab bataएं तैयबा. Sir, अब बताएं. Nobody corrected me. I'm just moving on, expecting that somebody will tell me. Nobody's telling me anything. Sir, this is not butan 1-on. No. Because see, this carbon is bonded to a carbon and bonded to an oxygen, which means that this bond is with a hydrogen, and this is not butan 1-on. There's no such thing as butan 1-on. What is this fella? This is meth-eth-pro but. This is what? Butanol, and we ignore functional group isomers, although these two are isomers. They are functional group isomers. This is a hydrogen bond right here, sir. Please, these things are important. Sir, bas baat lagani thi. No, I was just thinking that, Tayyiba said we got it. Yes, you are right. Sir, isn't this wrong? It is. Huma, you're absolutely right. I was just waiting for Tayyiba to speak. So, the recording just stopped for some reason. So, Tayyiba, this was for you. I was waiting for you to say something, but you didn't. Which means, Tayyiba, be a little more attentive now. Right? So, remember, these are isomers. But this is not butan 1-on. There's no such thing as butan 1-on. It's butanol. They are isomers for each other. But remember, what do? We ignore functional group isomers for the examiner. So, we ignore the functional group isomers for the examiner. And then, if you look at this fella right here. If you look at this fella. What do you call this? Meth-eth-pro. Right here. Meth-eth-pro. Right? And on the second carbon, you have the double bonded to O. So it's meth-eth-pro. Propan 2-on. And which fella is this? 1, 2, 3. So it's 2-methyl propan 2-one. Right? 2-methyl propan 2-one. And this is absolutely possible. And no, it's not possible again. Why? Please, 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 please. Look at this middle carbon, guys. How in the hell can you put a CH3 on top of this? Because a middle carbon cannot make more than 4 bonds. These things you need to remember. Middle carbon can make how many bonds? 1, 2, 3, 4, 5. Is the middle carbon like some sort of superhuman? So that's also not possible, sir. This is not possible. So the only thing that you need to understand is 4-carbon ketone does not have any isomers. No isomers. No, it only has one name. Yes, it does have a functional group isomer. Yes, it does have a functional group isomer. Butan 2-one and butanol. But if the examiner asks you, you need to ignore functional group isomers. You need to ignore functional group isomers for your exams. Right? पकड़ लिया सर. नहीं, आपने नहीं पकड़ा था ये बात. Right? So please, you need to be very careful. You don't follow the CAN method blindly. Use your brain a little. I have to ignore functional group isomers. So although these two are isomers for each other, there's no such thing as saying, oh, it does not have any isomers. No, this is incorrect, saying it does not have any isomers. But for your exam, you need to consider only chain isomer and position isomer as far as all the groups or the families are concerned. The functional group isomers are there. You know that a ketone will always have the respective aldehyde as its isomer. There are 2 isomers for every ketone, and for every ketone with its respective aldehyde. Like for example, butan 2-one has an isomer with butanol. They are both isomers of each other, but they are functional group isomers. That's why I have to ignore them. I say there's only one name possible for butanone, which is what? Butanone. You don't even have to put the position 2 here. Just call it butanone. That's it. Because we know there's no such thing as butan 1-one, right? So you call this what? Butanone. ONE. You just add the ONE because there's no such thing as butan 1-one, right? So butanone is the smallest. Is the fella that can exist. There's no such thing as butan 2-one or 1-one. It's just butanone. Just like whenever you are saying, right here, whenever you're saying, let's suppose, whenever you're talking about alcohol, a 2-carbon alcohol, you don't say it is ethan 1-ol, are you? You're just saying it's ethanol, because there can't be, ethan 1-ol or 2-ol. It's just ethanol right here. So this is just butanone. Don't put 2, because there's no point in putting 2. Right? It's only butanone. But remember, keep this in the back of your brain. Sir, pakda hai. Sir, aapne message nahi dekha. Where? Oh, acha. Tayyeba got this. So please don't follow the CAN method blindly. That's what I wanted to give you guys from this. Right? Chalo, let's start. 5-carbon ketones. Shaba. 5-carbon ketones. How many names are possible? Excluding functional group isomers. Exclude that. That's my assumption. I want you guys to exclude it. Chalo, do it and then we'll call it a day. Chalo, shabas. Tomorrow we'll do cycloalkanes naming. Yeah. This fella is incorrect. Use the same CAN method. Just make sure if you go from a ketone to an aldehyde, by taking the carbonyl carbon on the terminal carbons, don't take that in your answer. Because the examiner does not expect functional group isomers for you to identify functional group isomer. Yes, if it comes in an MCQ and you must be able to quickly say, okay, Sir Sulman told us that a ketone always has a respective functional group isomer of an aldehyde. But normally, when they say to identify an isomer of a ketone or an aldehyde, you just have to look at the chain and the position. That's it. And make sure that when you switch the position and it becomes an aldehyde, you don't take that into consideration. And God knows why they do that. God knows. They just say we don't expect students to know functional group isomerism at this point. And normally, isomerism for ketone and aldehyde isn't tested in your exams. I'm just going beyond the exam scope. If ever it were tested, if ever, right? So a 5-carbon ketone, test it for me, please. Tayyaba is smart. She caught on to the other one. So it's my time to shine, and it's my time to do it. Ibrahim, you're you're awesome. You're right. Fatma, you're also awesome, but you just missed on one. Let's look into which one Fatma missed on. Think about it, Fatma. Till we do it, maybe you catch on to it. 5 carbons ketone, 2, 3, 4, 5. I'm gonna do skeletal for this. 4 carbons then, 2, 3, 4, 3, and then 2, and then 1. I know 3 and 1 and 2, we just ignore them. Ignore them. Ignore. Right? Now come on to the first two. Because if I put a CH3 right here, where in the hell would I put a CH2? A carbonyl carbon. If I put it here, it becomes aldehyde. If I put it here, it becomes aldehyde. If I put it here, it's not possible. Why? Because 2, 3, 4, 5, 1, 2, 3, 4, 5 carbon can't make 5 bonds, hence ignored. Hence not possible. NP. If carbon were to make 5 bonds, then this would probably also be an isomer. So how many different names, and what are those names? Let's look into it. Yes, now you're right, Fatima. Awesome. So 5 carbons, right? So 2, 3, 4, 5, and it's a ketone that we are talking about. So can I put a carbonyl carbon right here? No. Why? Because it becomes an aldehyde, and the examiner tells us to ignore aldehydes. Can I put a carbonyl carbon right here? No. Because why? Then it becomes an aldehyde, and the examiner tells us to ignore aldehydes. So I can't put the carbonyl carbon or the terminal carbons. Why? Because it becomes an aldehyde, and although they are functional group isomers, the examiner does not expect us to know them, and hence ignored. Done? Now I can play around with these two fellas. I can put the carbonyl carbon on the second carbon right here. And the moment I place it on the second carbon, it becomes meth, eth, pro, bute, pent. It's what? Pentan, 2-one. Pentan, 2-one. And I can also place it on the third carbon, right here. And I can also place it on the fourth carbon, but if I place it on this carbon right here, then it becomes the same as this carbon. So this and this becomes the same. So I can either place it on the second one or on the third one, because the fourth is effectively the second. It's just mirror images of each other, because then you start numbering from the left to right hand side, right to left, right? So this is one fella, and the second fella that can exist is 2, 3, 4, 5. 2, 3, 4, 5, right? The second fella that can exist is this right here. So one is pentan 2-one, and the other one is pentan 3-one. This is highly unlikely to be tested in your exams, by the way. I'm just teaching you guys. Okay, if it were ever to be tested for some reason, I've seen one question, I think, where the examiner ignored functional group isomer for it. And I think I even wrote to the examiner, to Cambridge, but I never really got a response. But then I'll go to some sort of training and ask them why they don't do it. I think the reason is the same which I am telling you, which is probably they don't expect you guys to think this deep. But then in MCQs they do. So what's the problem? Right? And if you look at the 4 ones, 2, 3, 4, you have an add-on. You have 2 add-ons. You have a CH3 as the add-on, and you have the double bond O as the add-on. So we always put the CH3 first and check to not change the length of the carbon. So if I put a CH3 here, the length is changed. If I put a CH3 here, the length is changed. If I put the CH3 here, the length is the same. If I put it here, it's the same as putting it here. So I'll just put it here and lock the structure. Put it here, and then this structure is locked. Now I can put the double bond here. No, I can't, because then it becomes an aldehyde. Although it is still, although it will be your isomer, but it'll be a functional group isomer. So I won't be required to do it, and even if the examiner asks you, also write the functional group isomers for it, he specifically mentions it, you can absolutely do it, because you know a systematic way of doing it. You're not doing guesswork, right? So if you put the double bond here, it becomes what? Aldehyde. So why I'm going to ignore that. If you put a double bond O here, it becomes an aldehyde. Ignore it. Now the only possibility is putting a double bond O here and putting a double bond O here. If you put a double bond O here, that's not possible. Why? Because carbon can't make 5 bonds. 1, 2, 3, 4, 5. Carbon can't make 5 bonds. So that's also not a possibility. The only possibility of putting a double bond O is right here. See how easy is it? It's like puzzles. You guys will be genies, gurus. Sir, W-can method. Thank you, Ibrahim. So now you start numbering. From which side? Where the functional group is the closest. This has no preference when you have functional group. So when the functional group is the closest, so this is what 1, 2, 3, 4, and what is it called? It's called 3-methyl. On the third carbon you have methyl, and then it is meth eth pro but, and it is butan 2-one. So it's 3-methyl butan 2-one or 2-butanone, same thing, right? Because it's on the second carbon.